So far this year, we've done all of our work with right triangles. The trig presented this year works only if the triangles you are working with are right triangles. But as you know, in real life, not all triangles are right triangles. So starting today, we're going to learn, what do I do if the triangles aren't right? Can we still use trig to help us solve real-world problems? The short answer is yes. We can use what's called the Law of Cosines and the Law of Sines to help us apply our trig functions to non-right triangles. The first law we're going to learn is the Law of Cosines, which basically says for any triangle, you can use the following formulas. The first thing I'd like you to notice in this formula here should look familiar to you. It's the Pythagorean theorem. Pythagorean theorem, again, only works for right triangles. However, if you have this little add-on, it helps the Pythagorean theorem apply to non-right triangles. So the Law of Cosines is just a changed up version of the Pythagorean theorem. I want you to notice a few things about this pattern. There are three formulas here. They're all actually the same formula, just different depending on which side or angle you're working with. Look at carefully though, in the formula, if you have side A by itself, you have angle A over at the end. Whereas if you have side B by itself, you have angle B, side C, angle C. Inside, you have the two sides that aren't the one that's all by itself. So if the A was by itself, now you have the B and the C kind of in the middle there. If you had B all by itself, now you have the A and the C all in the middle, etc. And then attached to the cosine, you have the same two sides that you had right there. On a test or a quiz, I'll give you one of these formulas and expect that you should be able to adapt it to whatever you need based on whatever side you're looking for. Basically, if you're looking for side A, use the formula with A all by itself. If you're looking for side B, use the formula with B all by itself, etc. If you're looking for an angle, it's better to use what's called the alternate form. It's exactly the same formula. I just manipulated it algebraically so that the cosine A was by itself. Everything else is really exactly the same. Notice again that the angle that's all by itself matches with the negative side. So that's how you can kind of remember which ones go where. The angle and the negative side go together, whereas the other sides, B and C, are on the top and the bottom. If I wanted to rework this formula for, let's say, angle B, I would have cosine of B. And now the negative side would also be B to match the angle. And then I would put A and C in the other spots. So let's start talking about some applications here. First, I want to show you that this really is something that works for every angle. It also does work for a 90-degree angle. So my first question is, does the law of cosine work for 90-degree angles? And hopefully our answer is yes. Let's start by drawing a picture. So here I have a right triangle. So let's start filling out our formula for b in this case. So I'm going to say that b squared is equal to a squared plus c squared minus 2ac cosine b. So that's my formula. Now, the only thing I actually know about this triangle is that b is 90 degrees. Everything else is still vague in terms of letters. So the only thing I can replace here is cosine of 90. What is cosine of 90? So remember our graph. Now we're in degree mode instead of radian mode, but works the same way. This is a full circle, 360. So here we have 180. Here's my 90. Cosine of 90 is 0. So in my formula, I can replace cosine of b with 0. This works out really nicely because 0 times anything is 0, and that whole piece goes away. And I'm left with b squared equals a squared plus c squared, which, even though it's in a slightly different format, is the Pythagorean theorem, which we learned a long time ago works for all right angles. So basically, we just used the law of cosines to prove that the Pythagorean theorem is still true. Now we're going to start solving triangles. Here's an example of a triangle that has what we call SAS information. Basically, that means you're given two sides and an angle in between them. Whenever you have an SAS triangle, you're going to use the law of cosines to help you finish solving it. Solving a triangle means finding everything that's missing. So in this triangle, we're going to find side C and angles A and B. Starting with side C, we're going to use our formula c squared equals a squared plus b squared minus 2ab cosine c. We have A, which is 16, B, which is 10. So we're going to plug those in. Now this becomes a complete calculator problem. Make sure you're now in degree mode. And type 16 squared plus 10 squared minus 2 times 16 times 10 times cosine 110 in your calculator. Depending on how great of a calculator you have, you might have to do this in steps. That last part should all be multiplied together and then subtracted from 16 squared plus 10 squared. You should get something like 465.45. And then to get C, take the square root of both sides. And you get 21.57. Now, one thing to keep in mind with these problems is these problems have sort of a built-in check in that your answer should make sense. C is the hypotenuse, so it's the biggest side. So you should see that C is in fact the biggest side. Doesn't guarantee you have the right answer, but a lot of times if you make a mistake, you get an answer that doesn't make sense, like C would be too small, and you know you made a mistake and you can go back and check it. Now, we also need to find angles A and angles B. So we're going to use the same thing. We're going to start with our formula. This time I'm going to use that alternate version that allows me to have the angle by itself. So cosine of A equals B squared plus C squared minus A squared over 2BC. And you're going to plug in everything you know. Let's see, B squared is 10. Sorry. Careful there. So C squared is that 21.57 that we found a second ago. And once you have everything that you know in, this becomes an exact calculator problem again. You're typing in your answer, and out pops the answer. Not a lot of work left involved in this. So here you should get cosine of A equal to 0.7169. And then to get A by itself, you're going to take the cosine inverse of that and get 44.20 degrees. Now remember, there's going to be some rounding issues with these. Remember, we rounded back up with that 21.57. We're rounding again now. Expect that your answers, the book answers, my answers, might be a little bit different. Do the best you can to round as least amount as possible. So as we're going, if you can keep that whole number in your calculator, do it. Only round at the very end if you have to. That way your answer is as close as possible. But do expect that on occasion your answers are going to be a little bit off. The last thing we need to do now is find angle B. So we have C was 21.57. Angle A was 44.2. And you could use law of cosines again to find angle B, but that's a little bit tedious. You can use the fact that they add up to 180 degrees to help you out here. And you should get 25.8 degrees. So we've now solved everything missing in this triangle. So let's try another one. This time we're going to solve a triangle with SSS information. Same idea as the last time. Now we're just given 3 sides instead of 2 sides and an angle. When you see SSS given, again, it's going to be a law of cosines problem. But now we only have 2 angles to solve, no sides, so we're going to start right off with that alternate version. Cosine of A is equal to B squared plus C squared minus A squared all over 2 times B times C. Again, you'll be given the formula, so just have to plug it in and then type it right in your calculator. Should get cosine of A equal to 0.9269. Take the cosine inverse of both sides. You get about 22.05 degrees. We're going to do the same thing for another angle, so we can try cosine of B. This time we get A squared plus C squared minus b squared over 2 times a times c. Plugging in those formulas, type it into your calculator. You get cosine of b equal to 0.7346. Take the cosine inverse of both sides, and you get 42.73. Now that we have two angles, we can use the fact that they add up to 180 instead of having to do the law of cosines again. And you should get your last angle equal to 115. Now go back and check, make sure your answers are reasonable. A is the smallest side, so it should have the smallest angle. Then B. C is the biggest side, it should have the biggest angle. Gives you at least a suggestion that you're on the right path. Not a guarantee, but a good idea. Now let's try a word problem. Get us sort of the idea of why we would use this in a real life situation. Two trains leave a station on different tracks. The tracks make an angle of elevation of 125 degrees with the station as a vertex. The first train leaves at a speed of 100 kilometers per hour, and the second train travels at an average speed of 65 kilometers per hour. How far apart are the trains after 2 hours? We're going to start by drawing a picture and writing out some of the information since you now can't see the problem anymore. But we have a station here, and we have two trains traveling with 125 degrees in between them. So that was our given information. Train A, just for the record, is going 100 kilometers per hour. And train B is going 65. Basically, I'm looking for how far apart are they after 2 hours. So the first thing we need to figure out is we have one angle. We need more information in our picture. We know that train A is going 100 kilometers per hour, and it's been traveling for 2 hours. So this side should be 200 kilometers. Train B has been traveling at 65 kilometers per hour for 2 hours. So that's 130 kilometers. And what we're looking for is this side, we'll call S because I called the station S. So now, this is where the formulas get a little bit tricky. We have formulas for A, B, and C. Now I've thrown in this different letter. That's way confusing. Same process, though. Remember, if I'm looking for S, I'm going to use the other two sides for this whole part, and then just do cosine of S at the end as well. So don't let that letter being different confuse you. It's the same pattern. So let's fill in what we got here. We don't know S. A is 130. B is 200. And S is 125. Again, calculator problem, so get it out, type it in. Should get S squared equal to 86725.97. Take the square root of that. And you get that the distance is approximately 294.5 kilometers. One more problem here. A 100-foot tall antenna tower is to be placed on a hillside that makes an angle of 12 degrees with the horizontal. So you can see here I drew in my horizontal. 12 degrees is the incline of the hill. It has to be anchored by 2 cables from the top of the tower to points 85 feet up the hill, here, and 95 feet down the hill. How much cable is needed? So basically in this case I'm looking for this cable and this cable to see how much I need. Now, we have 2 triangles here, so we're going to have to work with both of them. We know that b squared is going to be equal to 95 plus 100 squared minus 2 times 95 times 100 cosine. And now we need the angle right there to plug into the formula. Careful with that. It's a little bit trickier to figure out. If the hill is inclining at 12 degrees, then the decline from the red line down the hill is 90 degrees would be the horizontal plus 12 degrees downward. So that angle is actually 102 degrees. 90 degree horizontal plus 12 degree incline. We're also going to need to find K, and so that's going to be 85 squared plus 100 squared minus 2 times 85 times 100. And then that angle, 90 would be horizontal, but I'm going up 12 degrees, so that one would be only 78 degrees. Those 2 formulas we're going to need to plug in to our calculators and get a B and a K. B equals 151.58. And K equals 117. We need those to be added together to get the total, which is 268.59 feet. Alright, so that's the end of our lesson here. What we want to do is now see if we can apply a little bit. Good luck.